So now to conclude SlideCast D, which discusses flame displacement in the context of linearized Navier-Stokes and linearized reactive flows. First, I want to discuss that displacement manifests itself in a rather peculiar, non-intuitive way in linearized field methods, as we like to call them. Linearized Navier-Stokes, linearized reactive flow. Imagine this is a premixed flame front in convective balance with an approaching flow. And let's imagine we add a bit of perturbation on the flow and we get a resulting displacement as a response to that perturbation. Now, if I consider a stronger perturbation, I expect a stronger response in the linear regime, right? The trouble is now if I add those two perturbations, those two signals, then the response to the sum of the signals, as you can see on this slide, is not equal to the sum of the responses to the individual signals. So the superposition principle is violated. And in that sense, displacement, if it manifests itself really as displacement in linearized fields method, would be nonlinear even at infinitesimally small amplitudes, because the response to the sum of the signal is not equal to the sum of the responses to the individual signal. So how do we see displacement? Well, let's consider the linearized convection operator, which is a scalar product of the perturbing velocity field and the gradient of the mean quantity. So if you consider temperature, for example, across a 1D flame, we see an increase from cold temperature to hot temperature. The fluctuation that results from a slight displacement of the flame in a downstream direction, for example, would be a negative excursion of temperature, as shown by the orange curve. On the other hand, a quantity like heat release rate in the flame, that is shown at the lower half of the plot, which have this characteristic decrease and then increase corresponding to the regions of positive and negative mean flow gradient of heat release rate. Now the interesting question is, what happens if I increase the strength of the perturbation? Do I then see a displacement of this fluctuation signal in a downstream direction? No, you don't. What you see is a stronger response, but with the same functional shape. And that is the perhaps non-intuitive, at least it bothered me when I saw this first time. Okay, now let's discuss the fluctuations of temperature, heat release, and entropy for a very simple 1D flame, not anchored, but simply in convective balance with the approach flow. And the dashed line here shows the mean heat release rate, so you have an idea where the flame is sitting. And what I'm comparing here is linearized reactive flow. That is a formulation where we take the governing equations of reactive flow and linearize it. And we linearize everything, species transport, chemical formation, we linearize Arrhenius, and so on and so forth. And from left to right, you see half a period of the oscillation. So the flame is simply displaced downstream. No modulation of the overall heat release rate results, right? We've discussed that case previously. And you see the temperature profiles as you would expect them. For the heat release rate, that's the red line, the characteristic decrease, increase with increasing time. Now, up to half the period of the oscillation, you have an increase in amplitude, but the shape doesn't change. The later half of the period, when the flame is convected back to its original position, you would see the same images, but simply in reverse order. The entropy also shows the typical decrease, the dent, so to speak. Temperature is a bit more complicated because you also have modulation of temperature through pressure, in isentropic fashion, so to speak. But overall, this seems to make sense, and it also agrees with CFD results, which are shown by the dashed lines, which which agree very nicely. Now, if we consider the same case with a linearized Navier-Stokes formulation, we see a few disconcerting differences. Well, first of all, heat release rate stays constant, is not perturbed, which first may seem unrealistic, but I remind you, overall heat release rate in this case does not fluctuate, so the flame transfer function is 0, so ln(SE) plus flame transfer function is just the same as ln(SE) without any flame transfer function, and we have also 0 fluctuation of the heat release rate. The temperature shows also overall decrease with the isentropic response to pressure changes. What is really worrisome is the entropy wave, or the field of entropy fluctuations, which very clearly shows fluctuation of entropy at the exit of the domain. That is, our linearized Navier-Stokes, in this case, generates an entropy wave where it shouldn't, because this is an ideal premixed flame as introduced previously. Okay, now Max also carried out a corresponding analysis for a 2D laminar premixed flame stabilized in a duct. So along the duct wall we had a hot section where the flame could stabilize. In the upper half you see the fluctuating heat release field with the LRF formulation. And these blue and red stripes, now you can imagine, you can read this, you understand how this describes a situation where the flame has been pushed downstream and outward by the velocity fluctuations. And if I start the movie, I can also see that I have these wrinkles traveling from the anchoring point to the tip of the flame, and I have an outward wrinkle and an inward wrinkle. This would be the outward wrinkle, and now comes the inward wrinkle again. Okay, the linearized Navier-Stokes, on the other hand, shows a very different picture. What one does here, I'm sorry, I was going too fast. What one does here, typically, one says, I have no detailed information about the distribution, the spatial distribution of fluctuations. So I distribute the fluctuating heat release rate in proportion to the mean heat release rate. And then the flame transfer function for global heat release rate would give a spatial distribution of fluctuating heat release rate in ln(SE) as you see it in the lower half of the picture. Okay, obviously very different. I don't see any wrinkles. I don't see any displacement with the ln(SE) formulation. Now, what are the consequences for entropy? Well, here you see results for the LRF. So the top picture has not changed. That's just heat release and wrinkles. And for entropy, lower half, we see there is a lot of entropy generation and annihilation in the flame region. But the entropy downstream of the flame does not fluctuate. This flame does not generate entropy waves. And indeed it shouldn't, right? ln(SE) on the other hand, now again, heat release rate from ln(SE) plus flame transfer function is shown on top. ln(is) generate entropy waves, spurious entropy waves, because I think I'm reiterating a point you've heard now many times. These ideal premixed flames should not generate entropy waves. And that's a pity, because ln(SE) would be ideal to transport entropy waves through the combustor to a choked exit, say, but if they fail at describing correctly the production of entropy waves by the flame, then I'm in a hopeless situation. Okay, to come to an end. I hope I have convinced you that representing flame dynamics in the time domain and in terms of the impulse response is really elucidating. It is more intuitive than flame transfer functions in frequency domain. It better helps you understand or identify the relevant timescales, and it better helps you understand how the various effects of flame displacement, flame movement, but also local effects without flame movement are interacting. And then also the other takeaways from this course, I hope you agree that we could resolve the Bauerheim paradox by distinguishing between a moving flame and a heat source at rest. I argued that ideal premixed flames should not generate entropy waves. And I guess my recommendation is if you have if you see a paper that includes a model for entropy waves, make a simple check. Does this model generate entropy waves for the case of an ideal premixed passive flame? If it does, then something is at fault with the model. I hope I could convince you that the paper with Lynn Strobio-Jen and Sebastian Bomberg on the linearized Rankine-Guignot flame movement is valid also for non-flat flames, although I do have to admit the presentation of ideas in the paper could be better. We have some additional evidence that convective velocity perturbations are a consequence of flame wrinkling and not of immediate acoustic to hydrodynamic mode conversion. And unfortunately, LNSE combined with a global FTF misrepresents local fluctuations of heat release rate and the generation of entropy waves. One could fix LNSE with a locally resolved FTF. That is also explained by the paper by Max Meindl. It's demonstrated, but it would be very hard to measure or cis-ID local FTF in the turbulent case. Okay, this brings me to my conclusion. You find these slides also on ResearchGate. The slides on ResearchGate also include a list of references of papers that I've discussed here. Thank you for your attention.